It's common practice to use recursion to solve certain types of programming problems. So a recursive function is one that calls itself. Usually this is in the context of creating a smaller version of the original problem until the problem is solved. So here's an example of the classic recursive solution to the Fibonacci numbers in C or C++. Okay, so let me start by showing what the Fibonacci numbers are. So remember, the first two Fibonacci numbers are 0 and 1, and then every other number is calculated by summing the previous two together. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and so on. Okay, so if I asked for the Fibonacci number with the index of 8, what I should get back is the value 21. Okay, so here's the C version. We have a function called fib. It takes the fib num that we're looking for, so 0 or 1 or 8, okay, and it's going to return the corresponding Fibonacci number at that particular index. Now, the way that most recursive functions work is we think of a kind of a base case and a general case. So the base case is when the problem has been reduced to such a small state where we can return one of the values. So if fibnum is ever equal to 0, we know that's the 0th value. If fibnum is ever equal to 1, we can return 1. The general case is how we eventually get to the base cases. So this is saying now we're actually going to recurse. So we're going to call fib from fib. But in order to get the current fib number, we're going to take fibnum minus 1 and pass that into the fib function. And then when that value returns, we're going to call fib again, this time passing fibnum minus 2. We're going to sum those two things together, and that's the value we're going to return. Now, each call is waiting for the next call to return a value, which it will then return to the previous call, all the way back to the original caller. So we can see a picture of this. Kind of looks like this. So if we ask for the Fibonacci number of 5 with an index of 5, well, first we're going to find the fourth Fibonacci number, and then we're eventually going to add that to fib 3. But of course, in order to figure out fib 4, we need to find out fib 3 plus fib 2. Fib 3, again, is going to result in all of these calls here. Okay, so you'll see there are a lot of calls. In order to find just the fifth Fibonacci numbers, each one of these boxes represents a function call. You see there's quite a few of them. Now, some people naturally think in terms of recursive solutions like this. There is a problem, though, with using recursion in general. Recursive calls require some resources. And in particular, a stack frame is pushed on the call stack each and every time a recursive function is called. So we've been talking about that call stack quite a bit lately. Right, so every single time we call a function, we generate a new stack frame and we push it to the top of the call stack. For very large recursive calls, the call stack may consume so much memory that holding all of these stack frames, that the operating system will actually kill the program for being a memory hog. Okay, so if I were to try and calculate the 1/1,000,000th Fibonacci number, well, if you were to look at the call stack, at its deepest, it would hold about 1,000,000 stack frames. And most operating systems won't let a single program's call stack grow to be that large. So one of the things the operating system does is protect the rest of the system from any programs that are using too many resources. So the chances are good that your operating system will kill the program well before the call stack gets to 1,000,000 elements. Okay, there are certain types of recursive calls where the last thing that the function does is call itself. When the last thing that a recursive function does is call itself, this is called tail recursion. And a smart compiler can detect tail recursion and rewrite it as a memory-efficient loop. Now in Clojure, the compiler can't detect tail recursion automatically, not yet anyway. Instead, the programmer has to explicitly identify these cases with the recur form. Okay, so I'm going to write the Fibonacci program in Clojure. Okay, so I'm going to write the fib function. It's going to use this helper, but we'll come back to that helper in a second. Fib takes a single number, and we're going to call the fib helper, but we're going to pass in 3 parameters. The first two are the first 2 numbers, so 0 and 1, and then this last number is the number that we're looking for. So if we're looking for the 8th Fibonacci number, n would equal 8. And I put a series of calls here to test my fib function. And I even use my map. So I'm going to create a range from 0 to 9, and I'm going to pass each one of those values to the fib function, and map should collect those results. Okay, so it looks like our Fibonacci numbers are correct here. And here's what map returned. Let's take a look at that fib helper. So having helper functions is a pretty common thing to do when you have a recursive problem that you're trying to solve. So here's a function called fib helper, and it takes the current number, the next number, and the nth Fibonacci number, the number that we're looking for. So remember, in fib we pass in the first 2 numbers, okay, and then the number that we're looking for. So all this function does is it does a little check here. So it checks to see, is the nth fib number, is that equal to 0? So there is a function called 0 with a question mark that return true if the parameter is 0 and false if it's not. If so, if the nth fib number happens to be 0, what we know is that the current holds the correct value. So when we called fib with a value of 0, like we did here, fib helper got 0, 1, and 0. Okay, and current just happens to be the fib number at position 0, so that actually worked. Now, if nth fib number is not equal to 0, right, this is where we're going to recurse, or at least this is actually a simulation of recursion. Okay, so we use the recur form. Okay, but now we have to generate the next 2 Fibonacci numbers. So we're going to take next, and we're going to make that the first parameter. In other words, what's in next now is going to be inside current for the next recursive call. Now next is supposed to be the next value, and we always get the next Fibonacci number by summing the previous 2. So current and next are the kind of the 2 previous values. If we sum them together, pass them into next, that'll be the next Fibonacci number. And then what we're going to do is decrement the fib number that we're looking for. So there's a dec function that's short for decrement that just takes 1 away. So if we were looking for the 8th Fibonacci number, basically what we're doing is we're recursing. We're going to do this about 8 times. And the most important part here is where we're summing the current and the next together to get the next Fibonacci number. Okay, and again, that I urge you to take a second to prove to yourself that this actually works. Okay, pause the video if you want and look at this code. But this, looking at the output here, it looks to me like it is definitely working. Now, using this recur is really kind of simulating recursion. Okay, so when you use recur, this does not get turned into an actual recursive call where we create another stack frame and push it on the call stack. Instead, it simulates it. So let me show you how we could do a similar thing in C or C++. So if you know about the C keyword goTo, which I hope you don't, you can probably imagine the tail recursive function call being turned into a goTo statement. So goTo is very bad in general, and you should never really use it. It produces spaghetti code that's almost impossible to comprehend. But using it does alter the flow of control to jump to a block of code without using the call stack. And this is what's going to save us from blowing our stack in a large recursive call. So let's look at a C version of fib helper. So it also has a current, a next, and a fib num. Now what we have here, this is called a label in C or C++. It's just a name with a colon. And what this does is it basically gives us a point to jump back to. So at any point, if we want to, we can go to the label called start, and the flow of control will immediately jump back to this particular line and start with our sequential flow after. Okay, so now what this fib helper does is it checks to see, well, is fib num equal to 0? In other words, have we worked our way down through all the fib numbers? And if so, current is going to hold the current Fibonacci number. If that's not true, right, if fib num is not equal to 0, this is where we're going to simulate the recursive call to fib helper. Okay, so we're actually not going to call fib helper. We're going to use our goto statement. But before we do that, we have to update the local variables, and this is kind of like resetting the parameters. Okay, so we set current equal to next, we set next equal to the sum of current plus next, and then we decrement, this should be fib num. Right? Okay, so this was almost exactly what went inside the parameters to recur. Right, there's next, current plus next, and we decrement that. Okay, then here's where we're actually going to simulate the tail recursion with this goto start. Like I said, the flow of control is going to immediately jump to this label. Okay, and the flow of control is going to pick up on this line, and we're going to check, well, is fib num, which we just decremented, is that now equal to 0? And if so, we'll return current. If not, we'll go through this process again and perhaps jump up here. Okay, so we used goto to kind of simulate a recursive function call, but without the overhead of actually creating a stack frame and pushing it on the call stack. Now in Clojure, we also have this thing called a loop form. So there's this function called loop, but it acts more like a local recursive function call than an imperative loop. Okay, and the syntax is it looks something like this. We have loop, we have a group of bindings, and then we have some expressions. Let me show you how this is used in Clojure. Okay, so this is a function that is supposed to get some values and put them in reverse order inside a vector. Okay, so I'm going to call this function, I'm going to pass in the value 5. What I'm expecting to see are the values 5, 4, 3, 2, and 1. Okay, and that's exactly what we see here. Okay, so let's see how this loop works. So we have a function, we're passing in that number, 5. Okay, and here we have the form loop. And the first thing we have is a set of bindings. So again, these are kind of like local variables. We're setting this thing called result initially to be an empty vector. And current num, we're setting its initial value as nums up to. Okay, so this is very similar to a let, okay, a binding, where these are just the initial values that we're assigning to these. Then we check to see, well, is the current number equal to 0? If so, we're going to return result. Remember, result is that vector that's supposed to have all the numbers in reverse order. If the current number is not equal to 0, here we're going to use recur again. And in this case, recur, since it's inside a loop, it's not going to recur into the function. It's going to recur into the loop form. And what we're going to do here is conjoin. That means add something to the result vector. We're going to add the current number to the back of the vector. Then, okay, so that's the first parameter. That's the new value of result is going to be the conjoined, the old value of result plus the current number conjoined to it. Then we're going to decrement the current number by 1. so that eventually we will get down to 0. And when we do get down to 0, result should hold all of the values in reverse order. So for example, the first time we call the function, result and current number look like this. Okay. And since current number is not equal to 0, we conjoin 5 to result, and then we decrement the current number, so it looks like that. Then we recur, right? And this is not 4 is not equal to 0 either, so we conjoin it and decrement. And we do this again, and again, and again, until the current number is equal to 0, in which case we just return the result, which holds all the numbers in reverse order. Okay, so in C, of course, we could do something similar, but it would look more like this. Have a function that takes a vector and a number, and we just continually push back the number, decrease the number, and then recur again. And again, this is okay. We're passing this by reference, so we're not making copies of the vector, but we are generating stack frames that are getting pushed on the call stack. If you're inclined to think in more of an imperative style, then you'd almost certainly do something like this instead. That doesn't use recursion at all. Okay, so the loop form is really just a way to do recursion on a more local scale. Since it's a form of tail recursion, it does not have the overhead associated with traditional recursion. Okay, so that's my discussion of recursion and closure. And again, if you use the recur form, you get all the benefits of recursion without any of the overhead associated with it.